Hello, and welcome back. Today we'll be starting GJK. Our goal is to come up with an algorithm that takes in two convex objects and returns both the distance of the objects and a way to compute the closest points. We will be solving the problem using the Barycentric and Voronoi approach presented by Erin Catto at GDC 2010. Similar to the presentation, I'll cover some theory and math concepts that will help in the solution, then put it all together in the GJK algorithm.
Starting off here, we're given a line segment and a query point. We would like to be able to compute the closest point on the line from the query point. Then using that closest point, we can then determine the distance between the query point and the line segment. At first glance, the closest point on the line that contains the line segment would be a projection of the query point onto the line. This becomes useful when we carve up the plane into its Voronoi regions. One for vertex A, one for vertex B, one for segment AB. If we can determine the region that the query point is inside, we can easily compute the closest point on the segment. In order to find the projection of Q onto AB, we'll compute the barycentric coordinates of Q with respect to the line segment. To quickly cover barycentric coordinates, they are a normalized way to describe the contribution of a set of points in a simplex. They have many useful properties, but the ones we'll be interested in today are as follows. Barycentric coordinates remain invariant under transformation, meaning that if we calculate the barycentric coordinates, or weights, in one space, the same weights may be applied to the simplex in another space. We'll also be interested in the fact that if the coordinate is negative, it means that the corresponding point is separated from the query point by a simplex of a lesser degree created from the remaining positively weighted points. Let's say we have the point G, which represents the projected point Q onto the line containing AB. G is computed from the contribution of the weights from point A and point B. If G is off to the center here, then the weights of A and B would each be roughly 0.5. If G is to the left region, A becomes larger than 1, roughly say 1.25, and B becomes negative at about negative 0.25. Finally, if G is off to region B, we would switch and say B would be around 1.25 and A would become negative 0.25. However, in all of these cases, each sums up to 1, meaning that the weights remain normalized. In order to compute the weights for A and B, we want to create subsegments AG and GB, and then dot these subsegments onto the segment AB. The result from this dot product is then divided by the magnitude of AB to yield the fractional length that the subsegments span over the main segment. In fact, we don't even need the point G in order to calculate the weights U and V for A and B respectively. This is because the segment QG is orthogonal to the line segment AB, and the value of the dot product of AB against Q remains unchanged to that of AB against G, since the orthogonal components are ignored. Once U and V have been computed, we can bring back in the Voronoi regions and inspect the barycentric weights to determine which region the point Q projects into. We can determine if the point projects into either vertex region A or B. For example, if we have point Q here in vertex region A, because of that, the greatest weight B could be is 0, which means no contribution. So so we would simply return the point A as the closest point on the segment. However, if Q were to be here in edge region AB, then both U and V would have to be greater than 0 as they both provide some amount of contribution to the projection point G. And we return G directly as the weighted contribution of A and B as the closest point. Basically the same setup as last time. We're given a triangle and a query point, and we would like to be able to compute the closest point on the triangle. If we go ahead and divide the triangle into its Voronoi regions like before, we'll end up with 3 vertex regions, A, B, C, 3 edge regions, A, B, B, C, C, A, and 1 face region, A, B, C. We're still going to be using barycentric coordinates, however this time we'll need to compute them in a different way. We can still use the edge information to determine if the point is inside a vertex region. However, just relying on edge UV values is ambiguous as to which side of the edge the point may be on. And it also lacks the ability to report if the closest point is inside the face region of a triangle. Instead, this time we're going to calculate the weights UV and W with respect to the triangle as a whole instead of just its edges. We can do this by computing the fractional areas of the subtriangles, and then dividing it by the main area of the triangle. Unlike the line segment case, giving the sign fractions isn't as simple as the dot product. Instead, we'll compute the cross product of the subtriangle, and then dot that with the normal of the primary triangle. This gives you the scalar triple product, which correlates to the volume spanned by the parallel pipette of the subtriangle and the normal. If the volume is positive, then the input triangle is in the same direction as the primary triangle normal, and we can say that the subtriangle area is positive with respect to the primary triangle since their winding order is the same. This is useful because we can now tell which side of any given edge the query point is on. Now is the time to illustrate that barycentric coordinates and Voronoi regions are not the same thing. Let's take this triangle with points A, B, and C, and we're going to be examining vertex B. The Voronoi region of segment AB extends infinitely along the perpendicular region bounded by the vertices A and B. The barycentric regions extend infinitely parallel along the line segment containing A and B. Then likewise the same holds true for segment BC and CA. In this case, we can see that there's some overlap between what the barycentric coordinates consider to be the vertex region and what the Voronoi region dictates to be the edge. In order to account for this, we want to make sure that we first consider the vertex regions. Considering the vertex region is simply a matter of ensuring that the complementary UV coordinates of their line segments are negative. If, for example, both UCA and BAB are negative, then we know that the closest point lies in vertex region A. Likewise, if UAB and BBC are negative, then it would be in vertex region B. And finally, if UBC and BCA are negative, we've landed in vertex region C. Determining the edges is now possible as well, since we're able to compute the signed area. We'll end up making sure that the UV segments are both positive. This tells us that the point is somewhere within the edge. And then we'll make sure that the weight of the complementary point to the line segment is also negative. If the weight is negative, or at least 0, that means that the point Q is outside the edge and has a reverse winding order. So for example, if UV, AB are both positive values, we would check if WABC, or the weight of vertex C, is negative. Again, we do the same for the UVs of BC and check for UABC, and then the UVs of CA and check for the ABC. Finally, if all these pass, we should be in the face region and just make some assertions that all weights for triangle ABC are positive and add up to 1. So now is also a good time to introduce the next concept before moving on to the tetrahedron case. If you recall, the primary goal we're trying to achieve is to detect that two objects are colliding, as well as a way to get back the closest. We can achieve both of these by working with something called the CSO, the configuration space obstacle. A nice property about the CSO is that if it contains the origin and configuration space, then we know that the two objects which yield the CSO are colliding. We can think about this intuitively by inspecting vertices on the CSO. These vertices are a combination of the subtraction of two support points found on the objects. The support points are the most extreme points in a given direction. By computing the support points in this way, we can examine the points on the CSO which lie on the convex hull. We do not compute the entire CSO, however, we do it one point at a time. We do this by creating a 0 to 3-dimensional simplex to represent the current inspection of the CSO. Every time we add a point, we evolve the simplex until we either terminate or detect containment of the origin inside the configuration space obstacle. This solves the first goal, determining collision. The second goal can also be solved, again, by using the CSO. Since we compute the closest point using the barycentric coordinates, we can store the vertices of the two objects which create any given simplex vertex, and then by summing each object point with the corresponding vertex weight, we can get back the closest point on the corresponding objects. So now that we're acquainted with why all this theory helps us solve our goal, it's time to move on to the final case, which is detecting if a point is inside a tetrahedron. We're no longer interested in what the closest point is, but rather just detecting containment of the query point. Just like with the triangle case, we need to consider the regions in correct order. Vertices first, then edges, then face, and then assert containment. Testing a vertex region is very simple. We can do this by checking if the dot product of the vector that spans the vertex in question to the query point with the vector that spans from the complementary vertex on the line segment containing the vertex is positive. And that was a mouthful, so for example, let's say we're checking for the query point being in vertex region A. We'll do this by checking the dot product of AQ with AB, AC, and AD are all negative. The reason this works is very obvious if we inspect the problem geometrically. As long as the point exists outside all three of these perpendicular boundaries, the point will be in the vertex region. Since the boundary is orthogonal to the segment, it is not until the point crosses the boundary cone that the vector AQ starts to align positively with the complementary vertices of the tetrahedron. If we detect all three segments project negatively with AQ, then we reduce the simplex to point A. Moving on to testing if the query point is within edge region AB. This time, we'll test if the vector AQ projects positively onto AB, and then we'll check if the vector BQ projects positively onto BA. We do this to ensure that the query point Q exists somewhere within the bounding segment AB. Next comes some very interesting linear algebra that took me quite some time to comprehend what's happening. We first compute the surface normal of faces ABC. We now have a bivector perpendicular to AB. We're now going to take that bivector and cross AB, which gives us a new bivector instead of a trivector. Since this bivector already contains AB, we didn't actually add in a new dimension. However, this new bivector is now orthogonal to both AB and the surface normal of ABC. Now, if the projection of AQ onto this bivector is greater than or equal to 0, we know at least from the perspective of ABC, Q exists in the edge region AB. Next, we'll repeat the same steps, but this time we'll cross the normal of ADB with AB to yield yet another bivector which points towards edge AB. Likewise, we'll also check if the projection of AQ onto this bivector is positive. If we determine that the point Q projects inside the segment AB and along the edge AB/BA of triangles ABC and ADB, then we can reduce the simplex to edge AB. Next is a much simpler task, testing the face regions. In order to do this, we want to determine if the face we're testing acts as a splitting plane between the query point and the complementary point in the tetrahedron. To do this with face ABC, we're going to test if the two parallel pipettes created with the face and the 2 points are oriented opposite from one another. Performing this check is rather trivial. We can use the scalar triple product again to get the oriented magnitude of each parallel pipette, which gives us AQ dot NABC and AD dot NABC. If the two volumes face away from one another, then the multiplication of both these scalar values is negative, and we've already determined that the face is now a splitting plane, and we can reduce the simplex to face ABC. Finally, if all of these tests for each combination of vertex, edge, and faces fail, then we've detected containment of the query point Q inside of the tetrahedron.
Now that we have all the theory and concepts needed, we can begin to implement the GJK algorithm with our design goals. So to start off, we have a function that returns a Boolean indicating true for separation and false for collision. The function will take in two objects, A and B, as well as an initial search direction, which may be arbitrary. We also take in a closest point, and in practice should pass in the simplex S and distance D to use their data outside of the algorithm. In fact, an optimization you could do that I didn't see during the collision query video is to simply use the distance computed during GJK, since it's already the squared magnitude of the CSO to the origin, which is equal to the distance of the object's enrolled space squared. We'll start by taking a look at the overall algorithm and then looking at the other functions that are being used. We are going to iterate until we reach a termination condition or hit the iteration limit. At the start of an iteration, we compute a support point R from A, B, and D. Then, we check if the current simplex already contains the support point. If it does, we return true for separation since we had to fail a previous containment check to get here. Next, we'll push the point onto the simplex to evolve it, and then we'll attempt to call any non-contributing vertices, and this will internally compute the closest point for us. After this, we check if the simplex contains the origin or not. If so, we return false, having detected collision. Finally, we'll compute the magnitude of the closest point and check to make sure we're progressing towards the origin. If we are not, again we'll return true for separation. If these checks fail, we update the direction and the distance for the next iteration. Now, let's take a look at the methods. First is finding the support point. The support point itself is the difference of the most extreme point in an object A when projected onto D and the most extreme point in an object B when projected onto negated D. For example, let's say object A is a capsule with points A and B, and object B is a hull with points A, B, C, and D. Now, if D is equal to I hat, then for A, we would be getting point B, and for B, we would be getting point A or C, and it's arbitrary depending on how the points are indexed, but we can assume it's probably A. Next, we'll look at checking for a repeating support point. To check if the point R exists in the simplex S, we can store the index value of the vertex from each contributing object and then check if the current support point matches any existing points. Moving on to calling the simplex, we'll start by using our barycentric calculations to compute the closest point based on the simplex degree. Then, we'll check if any weight on the current simplex is less than or equal to 0. If so, we'll create a new simplex of the remaining points, regardless of their value, and then recurse back into the function again until we terminate. Containment isn't too much of a challenge. We just need to consider the simplex degree and treat it like a collision test. In case 1, we do a sphere check with the simplex and the origin with the value of epsilon as the origin radius. Since the magnitude of S is the distance of the origin itself, just checking epsilon is sufficient. In case 2, we do a capsule check with the simplex and the origin by checking the closest point from the line segment to the origin, and this is not to be confused with the barycentric method. In case 3, we'll check if the distance component of the surface plane the simplex describes is less than epsilon. In all of these tests, if epsilon is greater than the distance, we roughly say the origin is contained since the objects would be close enough in world. Finally, for case 4, we return true because we previously couldn't call the simplex, indicating containment of the origin. Ran out of room, but we still need to cover updating the search direction. Again, we'll consider the simplex degree. Also, it should be pointed out that the simplex degree is actually one less than the number of points making it up. So case 1, for example, is actually regarding simplex of degree 0. For the first case, we simply treat the point on the simplex as the vector OS, and then negate that to find the search direction. In each case, we're going to want a vector that points towards the origin so we can converge in on it. In case 2, we'll use the same method as in the tetrahedron case, compute the cross product of the vectors AO and AB. This will give us the bivector of that plane, and then we'll cross back in AB to get a new bivector pointing towards the origin. Finishing off is case 3, and just like in the containment check, we'll compute the distance component of the plane the simplex describes. If the component is less than or equal to 0, we return the negated normal, and if it's positive, just the normal. And I always feel it's important to say that my planes are n.p plus d equals 0, so make sure to double check the aforementioned plane tests. There is no case 4, by the way, since we would have already terminated. That is all for today. Getting out the code next shouldn't take nearly as long. I vastly underestimated how much there was to cover and prepare for in this video. Nonetheless, thank you for your time, and I will see you in the next one.